JICA supports basic education in developing countries. JICA's previous experience in the provision of such support is showing that enhancing basic arithmetic skills is vital to improving students' academic achievement. How should teachers go about teaching basic arithmetic while ensuring that students experience the joy and significance of learning? These are all scenes showing children doing calculations. What kinds of methods are they taking? They might count using their fingers and toes. Draw sticks on a piece of paper, then bunch them into groups or erase them. And then there are those children who use neither method. They do the calculations in their head. In mathematics, Japan consistently ranks highly in international academic assessments, such as PISA and TIMSS. As such, the Japanese teaching method is attracting global attention. When we look at how addition, subtraction and other basic arithmetic is taught in Japan, we see that the system focuses on the composition to and decomposition of the number 10 for use in calculations. There is also emphasis on teaching the concept of numbers before actual arithmetic. It starts with concrete objects, moves on to semi-concrete or representational objects, before arriving at the abstract concept of numbers. In this video, we introduce Japan's experience in approaches and teaching methods for addition and subtraction, the most important elements related to numbers and calculation in arithmetic. Particular focus is placed on the content taught in the first year of elementary school. Formation of the concept of numbers. An understanding of the concept of numbers is first required to understand basic calculation in arithmetic. In Japan, emphasis is particularly placed on having children understand the concept of numbers. For example, in elementary school mathematics textbooks, children begin by learning the concept of sets. They are asked to find and group together objects and animals based on various perspectives that are the same or have the same characteristic. Next, students learn to compare the number of elements in a set using one-to-one correspondence. For example, students are shown an illustration of numerous dogs and balls. They are then asked, can all the dogs get a ball? To compare the difference in the number of dogs and balls. The children draw lines to connect each dog directly with a ball. In this way, they learn the meaning of having the same or different number. When lines cannot be drawn, an indirect method can be taken, like placing plastic bottle caps of one colour on the dogs and caps of another colour on the balls. The bottle caps are then lined up next to each other for comparison. Next, they focus on the number of elements in a set. For example, students are asked, is there a fruit or animal of the same number as the dogs? To find items of the same number. In this way, students are taught to see sets of the same number, regardless of the size or type of the individual item. Sets with the same number of elements are first created. Semi-concrete objects such as bottle caps are then made to correspond to the number of elements in each set. Finally, a numeral that corresponds to the number of elements is identified. Numerals representing the number of elements in sets are called cardinal numbers. Students learn to associate concrete objects semi-concrete objects and abstract numbers not only logically but also using their senses. When doing so, students are steered to think about semi-concrete objects in groups of 5 or 10. This process enables children to become aware of groups of 10. This is later utilized in carrying out calculations. Next, by composing or decomposing numbers, students learn to represent a single number as a combination of two numbers. Using concrete objects in the beginning can help them understand combinations. For example, 5 coins with 2 different sides are shaken, then scattered on a desktop. Students then count how many show heads and how many show tails. Students then use circles as counters representing the coins. When replacing those counters with numbers, students learn the correspondence between concrete coins, semi-concrete objects represented as counters, and abstract numbers. Through this activity, students learn that the number 5, for example, is a combination of various numbers. This is known as the decomposition view. At the same time, they learn that combining 1 and 4, or 2 and 3, makes 5. This is called the composition view. Developing this ability to see a single number as a construct through composition or decomposition is important for the formation of the concept of numbers. The composition or decomposition of numbers is continued sequentially from 5 up to 10. In Japan, there is particular emphasis on the composition to and decomposition of the number 10. This is because numbers are expressed using the decimal system. Numbers that make 10 when composed with a certain number is called a complement of the number. Complement numbers are an extremely important concept for addition and subtraction with carrying or borrowing, which utilize the regrouping principle. That is why students must fully master complements until they can automatically come up with the correct complement to a number. There are 8. How many more to make 10? 2. There are 6. How many more to make 10? 4. Teachers often use the first few minutes of a lesson in exercises to help students learn complements. This is to enable them to come up with the answer without even thinking. After students learn the concept of numbers and hone their intuition, they then go on to learn how to carry out calculations. Let's start with a look at addition. There are primarily 2 ways to think about addition: combining and increasing. Japanese textbooks have course units titled "How many have combined" and "How many have increased." This is to ensure that students are fully capable of carrying out single-digit addition without carrying. In this unit, they learn to recognize daily situations that require combining and increasing. They associate them with addition, learn how to express them mathematically, and how to calculate them. First, let's look at examples of combining. This asks, how many do we get if we combine something? Naomi has 3 pieces of candy. Takeshi has 2 pieces. If we combine both, how many are there? At this point, the teacher should not jump to using a mathematical expression to explain how to find the answer. Instead, candy, which is the concrete object in the question, is exchanged with semi-concrete objects, such as bottle caps, to allow the children to experience finding the answer. Actually moving the caps around while thinking helps children develop a greater sense of quantity. Furthermore, by exchanging the representational bottle caps with abstract numbers, the teacher makes it easier for children to understand the relationship between concrete, everyday situations and abstract numbers. By learning in this way, children develop the ability to do addition intuitively, not just by using their mind, but also their whole body. Now let's look at examples of increasing. This is a situation that asks, how many do we get if we increase something? There are 4 pieces of candy on a plate. If we increase this by 2 more pieces, how many pieces of candy are there now in all? Let's think about this again using bottle caps. If the caps increase by 2 pieces, that makes 6 caps in all. By using concrete situations and manipulating them similarly by using tools such as bottle caps, children understand not just intellectually but intuitively that combining and increasing represent the same thing: addition. Next, let's look at subtraction. There are 2 main ways to think about subtraction. They are taking away and comparing. Taking away means finding the quantity that is left after a certain quantity has been removed from another quantity. Comparing means finding the difference between 2 quantities. The meaning of the same subtraction formula can differ between how many are left and what is the difference. First, let's take a look at an example of taking away. This is a situation of how many are left. A plate contains 5 pieces of candy. If you take away 2 pieces from that plate, how many are left? Let's think about this using bottle caps. Out of the 5 bottle caps, we take away 2 caps. That leaves 3 caps. The mathematical expression is 5 minus 2 equals 3. The remainder is 3. This is taking away. Now, let's look at an example of comparing. This is the concept of asking, what is the difference between the quantities? The idea of comparing is more complicated than taking away. Careful explanation is therefore required. There are 8 people on the yellow team. There are 5 people on the green team. How many more people are on the yellow team as compared to the green team? Let's think about this using bottle caps. Line up the bottle caps for each person on a team. Here, there are 8 bottle caps for the yellow team and 5 for the green team. Of the 8 caps for the yellow team, if you remove the 5 bottle caps that correspond to the caps for the green team, there will be 3 bottle caps left with no corresponding bottle cap. The mathematical expression is 8 minus 5 equals 3. We see that the difference is 3. In this way, children learn that situations involving taking away and comparing can be expressed as subtraction. They develop the ability to understand the diverse meanings of subtraction. To to here, we have looked at instances where the numbers involved were less than 10. Now, let's look at instances where the numbers are greater than 10. Under the decimal system, if a child understands the construct of numbers from 11 to 20 as well as how to read the numbers, then they can basically use the same principle to understand two-digit numbers. This is why in Japan, once a child learns the numbers up to 10, they next learn the numbers up to 20. When learning numbers up to 20, it is important to make a group of 10. This helps make the children aware of the concept of a group of 10 and a number that does not reach 10. In other words, 10 plus how many? For example, if you show children plastic bottle caps scattered over a tabletop, the number of bottle caps cannot be instantly grasped if there are a lot of them. Children are asked what would make it easier. They are encouraged to draw a line around the bottle caps, or move them to make a group of 10. They can then see how many bottle caps cannot be made into a group of 10. This helps them think in terms of 10 plus how many. At this time, children are taught to write the number of the groups of 10 in the tens place, and the remaining number in the ones place. Understanding that the 1 and the 0 contained in the number 10 have different roles means understanding the decimal system. This leads to an understanding of positional notation. Without rushing students to learn abstract numbers, it is important to repeat activities to help students develop an awareness of groups of 10, and by doing so, have them do their own thinking and explain their thoughts using concrete or semi-concrete objects. Through such activities, children should become aware of the convenience of expressing numbers between 10 and 20 in the form of 10 plus how many, and how it makes things easier to understand. Building on what we have learned, let's move on to the addition of single-digit numbers that requires carrying or regrouping. Addition that requires carrying utilizes the ideas learned up to here. That is, groups of 10, 10 plus how many, and the composition to and decomposition of 10. When there is carrying, most children try to add by counting up using their fingers or other objects. This is known as counting on. Counting on is a very natural method for children to take. However, as numbers get larger, it becomes harder to remember how far they have counted, or harder not to make mistakes. Children may encounter difficulties at a later stage if they cannot leave behind the use of concrete items such as fingers and sticks to carry out calculations. When the concept of numbers starts to be formed in a child, they naturally develop the ability to perform mental arithmetic. However, children should carry out calculations using concrete or semi-concrete objects sufficiently until they naturally grow out of it and move on to mental arithmetic. Let's take a look at concrete examples. Naomi picked 9 tomatoes from the field. Takeshi picked 4. How many have they picked in all? The mathematical expression is 9 plus 4. Now, let's use plastic bottle caps to think about this situation. How can you make this calculation easier and more accurate?
9 only needs 1 to make 10. If you separate 4 into 1 and 3, you get the 1. So if you add that 1 to the 9, you get 10. The remainder is 3, so it's 10 plus 3, which makes 13.
The answer is 13. To make students understand this type of calculation method, it is important in the beginning to vocalize the process while moving the caps around. Now, let's take a look back at this way of thinking.
How many more does 9 need to make 10? 9 only needs 1 to make 10, so separate 4 into 1 and 3 to get the 1. Add that 1 to 9 and you get 10. Ten and 3 makes 13.
Then how should 3 plus 9 be calculated? One possible method is to think about how many more 3 needs to make 10. In order to arrive at the complement of 3, which is 7, decompose the number 9 into 7 and 2. The 7 is then added to 3 to make 10. The remaining 2 is then added to the 10. In this case, however, the 3 is smaller than the 9 being added, so it is easier to look for the complement number of the 9 to be added. That is why some children think in terms of, how many does 9 need to make 10? And then decompose the 3 into 2 and 1 for the calculation. It does not matter if the decomposition is carried out on the number that is added or the number being added to. What is important here is to always create a group of 10. In this way, when adding single-digit numbers that require carrying, find a complement of 10 for the number being added or being added to. Then, decompose the other number to create a 10 and how many situation. Emphasis is placed on learning this method. However, if a student is not used to finding complements, it takes them time to make a group of 10. That is why some children feel that it is easier to count up. The important thing is not to force children to use this method. They should experience how calculation can be made easier and faster by making groups of 10. Devise methods for making it easier for children to visualize 10 and how many situations. For example, by using bottle caps. Using diagrams to express decomposition for the purpose of calculation. Or creating groups of 10 by surrounding it with a circle. The important thing is to devise ways to boost children's understanding. While various textbooks are used in Japan, nearly all of them use 9 plus 4 or 9 plus 3 as an example when introducing addition that involves carrying. This is because it is easier to create 10 from 9 and utilize composition and decomposition for a calculation. As such, the numbers used in textbooks are selected in a way that makes it easy for children to become aware of forming groups of 10. Finally, let's look at subtraction that requires borrowing. Let's consider the following problem. There are 13 tomatoes. 9 were used in cooking. How many tomatoes are left? The mathematical expression is 13 minus 9. In the ones place of 13 is the number 3. 9 cannot be subtracted from the 3. So, how should this be calculated? The concepts of groups of 10, 10 plus how many, and the composition to and decomposition of 10 are again utilized. 9 cannot be subtracted from the 3 in the ones place. Therefore, 9 is taken from the 10. This leaves a remainder of 1. Combining that 1 with the 3 in the ones place makes 4. Hence, 13 minus 9 equals 4. The answer is 4. Let's look at this one more time. 9 cannot be subtracted from 3, so separate 13 into 10 and 3. Subtract 9 from the 10, leaving 1. Add the 1 and 3, making 4. To feel the usefulness of this calculation method, children need to be capable of quickly recalling complements of 10. Now let's look at another example of subtraction that requires borrowing, 12 minus 3. 3 cannot be subtracted from the 2 in the ones place of the number 12, so we can begin by first separating 12 into 10 and 2. 3 is then subtracted from 10, making 7. 2 is then added to this, making 9, which is the answer. But this is not the only way. The 2 in the ones place of the 12 is close to the 3 to be subtracted, so the 3 is decomposed into 2 and 1. Then the 2 is subtracted from the 12, making 10. The remaining 1 is subtracted from that 10, making 9. One's calculation methods that utilize the concepts of groups of 10, 10 plus how many, and the composition to and decomposition of 10 have been mastered, children can utilize them in various other settings that follow later.
いきなり足し算の仕方というよりも、その前にやはり数をどうやって把握するかっていった時に、その数の構成的な見方というのを非常に大事にしています。例えば、5っていうのはなんでそれが5って分かるかっていうと2と3でできてるよとか、7ってどうして分かるかって言ったら3と4だよ、いや5と2だよとか、あ、そっか、そうやって何かと何かで、その数を捉えていくと分かりやすいんだね。10を使わないでそのように処理することはできるんですけれども、それですとやはり間違いが多くなってくる。数の見方として10といくつって捉えてきた経験ですとか、そういうふうに10がいくつとか10といくつっていうふうに捉えることによっての良さというものを味わってきていますので、それを使っていくためにも、その10の構成的な見方を最初に丁寧にやっておくっていうことが大事なんだと思います。やはり数の構成的な見方を経験を積んでいくと、だんだんに指を使わなくなりますね。本当に7がどうあるのかなっていうのを捉えた時に3と4なんだとか2と5なんだとか1と6とか、そういう見方を何回も経験してますと、ブロックを分けたり合わせたりという操作を繰り返していくうちに、そのイメージが子どもたちの中にできるようですね。そうするとだんだんに手を使わなくなってくるっていうような、ことがございます。
As we have seen, when teaching basic arithmetic in Japan, the concept of numbers is first taught by making numbers correspond with concrete objects and semi-concrete objects. This gives children an intuitive grasp of numbers. Then, through composition and decomposition, children learn to see numbers as a combination of other numbers. This enables them to master the composition to and decomposition of the number 10. Later, when learning addition or subtraction that requires carrying or borrowing, the children learn how to utilize the composition to and decomposition of 10 in the process of calculation. The addition and subtraction introduced here is basic content learned during the first year of elementary school in Japan. Classroom teachers and university researchers in Japan have devised instruction methods and conducted research so as to enable all children to understand and master such basic content. By leveraging such practical knowledge gained from educational settings in Japan, JICA will continue its cooperation to enable all children in developing countries to experience the joy of learning and the joy of achievement.